All right, let's start just talking through Chapter 8 and see how it goes. And I hope you guys post any questions or email me with any questions. So, Chapter 8, we're going to start off with the two types of charges, and these are going to be electrical charges. And we give them names of positive and negative. Just think of them as names, because that way when we do magnetic poles, then we can just say like the North Pole and the South Pole are also just names. Right. One reason why we do call them positive and negative, though, is because the charges can cancel out. A positive one and a negative one put together would overall be neutral. The type of matter that we're familiar with is made out of protons, electrons, and neutrons. And so all atoms and molecules and people and houses are made out of different combinations of protons, electrons, and neutrons. Protons are teeny tiny particles, and they have a positive charge, and they also have a tiny bit of mass. Electrons are negatively charged and have an even smaller mass. Electrons have a very teeny tiny mass even compared to a proton. And neutrons are a tiny particle with about the same mass as a proton, but with no electrical charge. And I tend to think of a neutron as like an electron and a proton bound together. Right. Now, their masses and their charges, like how much charge do they have, is listed in a table on page 200, or, Google has it as well. But the units of charge, or at least the SI units of charge, is called the coulomb. So we might say there's 5 coulombs of charge, or 2 coulombs of charge. Or if it's negative, we could say negative 1 coulomb of charge. And it's abbreviated with a capital C. So here we can see the masses of the different particles in kilograms, and that negative exponent means really tiny. And here's the charge measured in coulombs. So the charge of an electron is negative 1.60 times 10 to the negative 19th. So it's also a very tiny value in coulombs. And a proton is the same charge, but positive. And there's the neutron with a charge of 0. Let's just quick go over kind of a cartoon version of a helium atom, just so you can kind of see how they're laid out. In the middle, which we call the nucleus, that's going to be only positively charged. We have protons and neutrons that can exist in the nucleus. All right, so here we would have, so the charge here would be twice of whatever the proton is. But there's also 2 neutrons in this nucleus, so that just makes this atom heavier. There's more mass in here. The electrons exist kind of outside of that, and you could call it the electron cloud. Sometimes we draw them as like little circles that look like they're on an orbit, and that's not realistic, but it's a handy cartoon. And this outer region outside of the nucleus is negative. Now for this helium atom, we had positive, or 2 protons, and we have 2 electrons. So overall, this would have no electric charge. Overall, it is neutral. Right, the +2 and the -2 cancel out. The electric charges can push and pull on each other, and similar charges will push away from each other. And that push that happens, we can call that the electric force. So if I had 2 negative charges fairly close together, they don't like being next to each other, and they will push away from each other. If they're able to move, they would move apart, but they might not be able to move. Also, if both of these were positive, so again, they're similar charges. This charge is the same sign as this charge. So again, they would push away from each other. Right. But opposite signs will attract, and so they will try to pull together. And if they're free to move, they will move closer together. So you could label it a pull if you want, but it is still the electric force. Right, and they would try to pull together. So if you've ever heard the saying like opposites attract, that applies here, and it's also going to apply for magnets. Now that amount of push or pull can be increased. Like it could push harder or it could pull harder. And the way you could do that is by increasing the amount of charge at either location or both locations. Right, so if you imagine instead of having just maybe one plus here, you had two pluses. So you're increasing the amount of charge. This pull would get bigger, so you could draw a longer arrow. They would be pulling together harder. Another way that you could make that pull stronger is just by moving them closer together. Right, they're kind of like gravity. The effect is stronger when they're closer together. Right, so if these two charges were closer together, that pull between them would get stronger. Right, and this works for magnets as well. So my headphones here have magnets in them, so they can stay attached and not twist each other, right, and not tie themselves into a knot. And if they're not very close together, you don't really even notice the magnets in them. But if you bring them closer, you can start to feel their attraction. And if you get them close enough, boop, they will have a stronger pull and keep themselves together. All right, so you could do this, you can imagine this with charge as well. Here's a quick simulation on PhET on the internet. So if you just Google PhET, it brings you to a bunch of simulations that you can just play with on the internet. So here we have a sweater, which has positives and negatives. So overall, right now, it's neutral. A balloon, that is also overall neutral. And a wall over here. Now, you can kind of charge up an object by using friction. So one way you can do that is to rub a balloon on a sweater or on your hair. And then some types of objects will choose to become positively charged and choose to become negatively charged. And if you want to know which ones are which, just email me and I'll send you a link. Now, I'm holding this balloon right now with my cursor, but if I let it go, is it going to be attracted to the sweater or repelled from it? Right, the sweater is positive, the balloon is negative. So if I let it go, boop, it's attracted. Now, if this simulation was written well, it should feel a stronger force when it's closer. But if I bring it further away, here, let me get rid of the wall. But if I bring it further away, it should not kind of slide over quite so fast right away. Yep. Right, so its acceleration, its rate that is going to speed up is slower, because when it's further away, it doesn't sense it as much. The force isn't as strong, but if you're closer, it gets pulled over quickly. Right? So Coulomb's law tells us how much force there is between two objects, depending on the amounts of charge that they both have and the distance between them. And so there's this constant here that you just plug in always. This would be the amount of charge on object one. So like on that sweater, how much positive charge was on that sweater? You would put that value in here and it should have units of coulombs. And then how much charge is on the balloon? How much negative charge is on the balloon in coulombs? You could plug in a number here. And this would be the distance between them in units of meters. And when you do this, it tells you how hard they are going to be pulling together or pushing apart, depending on whether they're positives or negatives. I'm not going to focus too much on this. Let's focus on some of the other qualitative stuff. There is a thing called induced attraction. So I'm going to show you an animation of that real quick. So for that, I'm going to bring back this wall here. So you would agree, hopefully, that this balloon is overall negative charged. And the wall is neutral. But if I force the balloon closer to the wall, the balloon is overall negative. So what the wall's molecules are going to do is the negatives are going to try to shift slightly away. The negatives in the wall will try to shift slightly away as much as they can away from that negative balloon, which leaves the positives slightly closer to the balloon. So then what this negative balloon does is it kind of forces this charge rearrangement in the wall, leaving the positives closer to it. And the closer charges have a stronger effect, a stronger force. So the negative balloon is kind of forcing an attraction to the wall. Right, so that would be induced attraction. Overall, the wall is still neutral, but that negative balloon has shifted them around a little bit. And this is kind of fun to do on a dry winter day. You blow up a balloon, you rub it on your hair or in your sweater a bit, and you get some static electricity built up on that balloon, and you should be able to get it to stay on a wall. And I just used the phrase static electricity, which really just means the charges aren't flowing. Static, not moving. Right? When the charges are moving, I think of electricity in a wire or getting a zap when you touch a doorknob and the static electricity all of a sudden can flow. Right? Then it's just electricity. It's no longer static. The idea of an electric field can be really confusing, especially since everybody talks about it or describes it in a slightly different way. I'm going to try to give it to you my way, which I think might be the least confusing way. But if you find another analogy or description, that's fine. So my description is that an electric field is going to be a map around some charged particles, maybe one, maybe several of them, showing the possible effect on another charge. And so maybe there isn't another charge there yet, but if you were to bring one in, what would happen to it? So I'll do another PhET animation. So what I'm going to do is I am going to bring a positive charge here and plop it in the middle of space. And these white arrows appear around it, and it's an imaginary map. An imaginary map kind of describing the amount of force that would happen on another positive charge. So I'm going to use this sensor now and drop it right here. So that red arrow would indicate the force that a positive charge would feel due to that original one that I had laid down. And we could imagine what would happen if I moved it closer. If I moved it closer, it would feel a stronger force. And notice that this red arrow is always going to be kind of parallel to these other white arrows, this imaginary map of white arrows. They're just kind of mapping out what direction the force would be if I could put another positive in there. What about if I had switched it to a negative? What would happen if I put a negative in here? Again, just by definition, our sensor, our imaginary kind of test case here is going to be a positive. So in this case, a positive would feel a force towards a negative. And if you move it closer, that force gets stronger. And if you move it further away, the force is weaker. And those white arrows are just a map showing that. And a fun thing that you can do then is kind of play around with different alignments. Like what if there wasn't just one negative? What if there were 3 negatives? Oops. That force, that imaginary map would represent stronger forces. And if you were to put a sensor in here now, the arrow would be longer than it was before. And our imaginary map on this simulation is kind of showing that by whiter arrows. What would happen if you had a weird arrangement of charges? Some positives and some negatives. What would the effect be on a positive? What direction would its force be around these different charges? And you can just play around with it and kind of see what this imaginary kind of positive particle would feel if you were just to move it around. So those white arrows are the quote-unquote electric field, our imaginary map. Now, how this animation shows the electric field is not really how we would just kind of sketch it out on some paper. So let me just show you how we would sketch it out on paper. So if we had a positive charge, we could ask what would its effect be on the space around it and try to sketch it out. So I'll draw some just solid lines. And I'm going to have these lines kind of be arrows pointing away. So this would be our charge. These lines represent the electric field map. So then we could say if a positive charge was right here, what force would it feel? Well, it would feel a force in that direction. And if a positive charge was closer, what force would it feel? It would feel a force kind of aligned with this map that we drew, the electric field map. But since it's closer now, the force would be stronger. So in the simulation, that stronger push was indicated by a brighter white arrow when you were closer to this charge. How does this map indicate a stronger push or a stronger pull? Right. Do you see here, closer to the positive charge, these lines are more bunched up? In places where the lines are more bunched up, you could say that that represents an area of stronger push. And out here, the lines are more spread out. So that would be an area of weaker push. So this kind of shaded area with pencil represents a region of stronger push. The lines are more bunched up there. And just kind of use your imagination and let them stretch out over here. If there was a positive charge here, well, the direction of the push is going to kind of continue along this line, that way. But it's further away out here where the field lines would be more stretched out. So I'm going to imagine it as being a small push, a weaker effect. And if I had a negative, what would its map look like? Well, we would imagine its map would look like this, with those lines of the map pointing towards the negative. And here, the lines are more bunched up again. So that region represents a region of stronger force. And if I was going to imagine a positive charge here, its direction of push or pull would be along this arrow, that way. It's out here where the field lines are kind of spread apart. So let's imagine it as a weaker force. And you could call it a pull. But if you were to draw it right here, closer, as a positive, it would feel the direction of the force kind of aligned with this arrow. And it's a stronger force. And so to indicate that, I'm going to draw a longer arrow. I know it goes through that negative right there, but this longer arrow just means a strong pull in that direction. And if you had a positive and a negative close together, let me just, for fun, show you what its electric field map would look like. Rough sketch. And then I would draw the arrows pointing from the positive to the negative. That's how we define our electric field map, is always pointing from the positives to the negatives. So then if I were to put a positive charge right here, which direction would it feel a push or pull? Its push or pull is going to be parallel to the electric field line right there. So it's either going to be to the left or to the right. The electric field line was pointing kind of in this direction towards the negative. So it would feel a push this way. If I were to put a positive here, it would feel a push or a pull this way. Let's call it a pull. And do you see where the lines are more bunched up? Where the lines are more bunched up, the forces are stronger. And if we drew little force arrows, those force arrows should be longer. So if we had a positive right here, what would it feel? It would feel a very strong push in this direction.